So let's start with our array again, and our analysis doesn't change from before, right? The only difference is Q's add from one end and remove from another, but we still want to avoid adding or removing from an arbitrary index. We want to try to access arbitrary indices and overwrite arbitrary indices. So what does this mean for our design? Step one, like before, create an array larger than we need. And then if we do like we did before, we can left justify our data just like we did with a stack, like this. So now the question becomes, where's the front? If this is the front, then enqueuing is super easy, right? We just enqueue, enqueue. But then dequeuing becomes a problem because we have to nuke this and then copy it down, right? And that's big O of n, so that's a problem. So we'll put our front over here, right? And then dequeuing is easy. We just nuke that, we nuke that, right? And our front moves back. That's easy. But now enqueuing is a problem because we're going to have to move this guy up and this guy up and this guy up just to be able to write here. So either way we do it, everything has to be shifted, and that's a big O of n process, which is slow and we want to avoid. So what do? Well, we just assumed that we had to left justify our data because it's convenient. That's the way we think about things. What if we didn't, though? What if we didn't left justify our data and instead we kept track of where in our array our data is? So we can keep track of our front and our back or our length. We can calculate one of these. We need to store two of these. But if we have our front and our length, we can calculate our back, right? And we can see that equation here. And if we just put, equals back, then with some light algebra, you can see that you could isolate any one of these three, right? I will tell you that from the front and the length, like you see, we can calculate back, or from the front and the back, we can calculate length. Yeah, from back and length, we could calculate front. I don't know anyone who thinks that way. Okay, I've never seen that happen, but it's technically allowed, so whatever. But just understand that typically we store the front and the length of the front and the back. And then once we have that, then actions just become writing to empty slots, right? We're going to write to the slot after the back when we enqueue, and then we're just going to add one to our back and increment it. And when we dequeue, we're going to nuke the slot at the front and then increment our front. Well, those are all big O of 1 operations. So we're back to good. Hey, the system works. What's the problem? Right now, it's not a problem, but let's walk through some operations, right? So we're going to start dequeuing and we're going to dequeue again, and then we'll enqueue a few items. And then we're going to get to a point where we're not going to have any more space. So what do? Option number one is we shift everything down, right? So 0.02 goes there and 85 goes there, or 0.2 goes there, and bar goes here and -15. But this is a big O of n process. And again, we want to avoid doing that if we don't have to. So let's avoid doing that if we don't have to. We could do that, or we could treat our array like a circular array, which means that once we move past the end, we can start adding to the front, right? We got these empty slots, let's just use them. So how do we know if we're in a standard or a circular configuration? Well, if we're storing the front and the back, that's real easy. If back is less than front, right, then we're circular, right? If we're calculating it, then we've got this calculation. Now our back index is front plus Q length minus 1. Well, let's imagine that we've got our front at index 2, an array of size 10, and 9 elements in our array. our back index is 2 plus 9, which is 11, minus 1 is 10. But we only have an array of size 10. Our back index is at 10, but our maximum index is 9. So what do we know? We know we have to be circular. We know that 10th element has to be at the front of the array. And that's true. If our back index is greater than array size minus 1, then we're circular. And think about it. 2, 3, 4, 5, 6, 7, 8, 9. We're at index 9, that's 8 elements. Element number 9 has to be at index 0. Beautiful. I don't bring that up just because I'm like, oh, here's some neat trivia, but because it's relevant to our next fact, which is the actual equation for finding the index of an element at the back of a queue, if you are not storing the last index, if you're storing the length, is this. Front of the front index plus the queue length minus 1 modulo array size. And modulo is a super useful operation if you have a functionally infinite amount of information that needs to be stored into a very discrete number of slots, because it'll cycle, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we're doing modulo 10, it's going to cycle through 0 through 9. We're going to get our indices every time, right? So if we do that same math, right? 2 plus 9 minus 1 modulo 10, right? This is 10 modulo 10. What's the remainder when you divide 10 by 10? It's 0. So the index for the element at the back of the equation is index 0. Let's go down one. Let's say we've got 8 elements. Right? Now we got this. 2 plus 8 minus 1. That's 10 minus 1. That's 9 modulo 10. Hey, the index of our back is 9 now, right? So that means that we start at index 2. We have an array where we start here, right? And everything from 2 to 9 is full. So where's the next slot going to be in that case? What's going to be index 0? We're going to write here next. Okay, cool. So what does that mean for the slot that we write to next? Well, we got to add 1. But the question is, do we add 1 here? Do we just nuke this? Or do we do this calculation and then add 1? And the answer is that we do the add 1 inside because we want to take that additional slot into account during the modulo, not after the modulo. If we did it after the modulo, remember, when we do 2, 8 minus 1, we get to 9, and we would get plus 1 is index 10. Whereas here, we go 2 plus 8, right? That's 10. Modulo 10 equals 0. And that makes sense, right? That's the logic we just saw. We want our next slot to be the first slot in the array. So that's how that works. So this is the equations we have to follow. But then resizing becomes a challenge, doesn't it? Because we can't just expand this array naively, can we? If we just expand this naively, if we just add slots here and don't do anything else, then yeah, we're going to have additional slots, but there's going to be 2 issues. One, these slots are going to end up in the middle. Notice that, that we're in the middle of our data. And 2, we haven't updated our front or our back, which means so we've got more slots that are eating up more memory that are empty in the middle, and we're still out of space. So that's not ideal. So what do we do? Right? what we do is when we reset the front of our queue, I'm sorry, when we copy our data, as we're copying our data, we reset the front of our queue to be at the beginning of the array. That way, we have control of it and things work out for us. So let's just imagine we have this array. 1, 2, 3, 4. Okay. And we're adding into it. And this is our back, and this is our front. Okay. And so we need to expand it. First thing we're going to do is expand. Right? And what we're going to do is go 1, 2, 3, 4, 5, 6, 7, 8. Great. So we're going to take our 3, we're going to put it here. And then we're going to take our 4, we're going to put it here. We'll take our 1, we're going to put it here. Take our 2, and we'll put it here. And now this becomes front, and this becomes back. And all of these are nulls, and now we have space again. So here's the question. Why? Why is this legal? Why was it so bad for us to do this before, but not now? And the answer is simple. We're out of space. We have to expand. The expansion is a big O of n process no matter what. The problem isn't the big O of n process. The problem is an unnecessary big O of n process, period. Flatly. End of story. Okay? This is not unnecessary. We need the extra space. And this is just a calculation, right? Determining the index where it goes is just some quick math. So if we're going to do that, we might as well reset the front anyway, because it saves us another headache. And then we're good to go. So let's see what that looks like in code. Again, all of this is available online. It's on the Canvas page. It's on the lab page, right? We're going to see our default capacity comes back, just like it did with an array stack, right? There it is. We have our length, which is the number of elements in our queue, and we have our front, okay? And our NQ, right? We do the same thing that we did before. Hey, are we out of space? If we are, we resize. We calculate where the end is going to be, right? What is the new slot, right? And notice here's our calculation. Front plus length modulo the length of the data, right? This is telling us how many slots are in our array. This is telling us how many elements are in our queue. Separate concepts. So what's the first position that holds data? How many slots have data in it? Modulo how many slots are available. And that's the place where we want to write. So we write to that slot and we increment our length. But let's take a look at this, since we just called that. This is a little more in depth. This is a little more intense, okay? So what do? We store the old data, right? Just like before, store the old data, okay? And then we're going to multiply our none list by the new size, right? So that's going to be, for instance, when we come in here the first time, it's going to be 20. Okay, cool. We're going to create an array of size, whatever the new size is. And we're going to overwrite our backing array with that empty data, but we've stored our old data. And then we're going to get our current index. That's our front. And maybe a better name for this is old data index, right? And we can overwrite that. Okay. And maybe we'll rename this new data index. Let's be explicit about this stuff, right? Okay, cool. So what's that mean? Well, we're going to get our old data index, which is the front. So we're going to start here, right? In this case, we'd have 2. And then we're going to do this loop once for every element in our old queue, right? The length of our queue, how many slots do we have? We have 4. So we're going to do this 4 times. And starting at index 0, right? That's our new data index. It's going to start at 0. We're going to set 0 to whatever was at the old data's front index, right? And then we're going to calculate our new old data index, which is add 1 to the old data index and then modulo the size of the old data. So we were at 2, now we're at 3. 3 modulo 4 is 3. Cool. Do the copy again. Great. We were at 3, now we're at 4. 4 modulo 4 is, oh, look, it's at 0. Now we're back, right? So we do that until we get to the end, and then we reset our front. And we have a new backing array. From here, things get relatively easy, right? When we when we dequeue, we grab the first element and we store it. We nuke what's at the front of our array. We calculate a new front, and because the front could be circular, we have to add 1 to it and then do that same modulo calculation that we did down here, right? It's the same idea. We decrement our length and we return the value. Or first, we can do it the different way. We can say, hey, is it empty? Is self.is empty? If it is, our queue is empty, and we're going to raise it. And when we raise something, it crashes, right? Boom. It's like a return statement. So we don't go past this. If our queue is empty, we're done. Otherwise, we return what's at the front element. And our len is just our length variable. So all of the benefits of an array and all the drawbacks of an array that we went over for a stack apply here. Okay. All of this additional complication might be hard for us to understand while we're learning it, but the math is the math, and computers are good at math. So this does not affect our runtime in any meaningful way. The only things that affect our runtime are how often we have to do expansions, and what affects our memory is the fact that it's got to be contiguous. Okay, but at least it's compact.